Okay. Let's hide it at the meantime. And bureaucratic questions of any type. Everybody is good. Okay. So we want uh, some people will like today's class, will find it interesting. Some people will hate every second, and maybe this class is overexposed of some painful point for some. And other will be okay with this, I hope. And for many of you, it will be absolutely trivial. And why am I explaining in such awkward way things that you already know? So yeah, let's talk about transformation. We are all preparing, in a sense, to homework one. We are still staying in 2D, but I'll try to pave the way to things that will also continue for 3D. Especially I'm talking about rotation matrix, but and why matrices at all, and so on. So we saw a transformation that shift a shape by taking the x, adding to the x4, taking every point and adding to the y, the elevation 4 as well. That was shift by xy. And at this point, I still didn't mention matrices at all. Then I talked about scaling, like scaling by half, shrinking it by half, taking the x, shrinking it by half, y, shrink it by half, taking the 0.66 to 3300, stayed where it is, very happy. And that was scaling in this case by Sx and Sy. These two constants are the same. Shearing, pretty cool. Shearing by along the horizontal direction. In this point, I look at the y value of a point, the elevation, and the elevation stays unchanged. On the other hand, the x value of a point, the new x value, x prime, is all the x value, x prime, but I'm adding to it also the elevation. So to the shift from left to right, the horizontal shift takes how high you are above the x-axis at the same point. So if you're on the x-axis, x stays the same x. This point doesn't go anywhere, this point doesn't go anywhere, the same that they appeared over there, while the higher we go, the more to the right we go. So this vertical edge turns to be an edge of 45 degrees slope. And this vertical edge that was with y equals 0, that was with x equals 0, now every point along the x-axis shift to the same point where the x is still 0, but I'm adding the y as well. That is, when I do this matrix multiplication, 1, 1, 1, 0 times xy gives me x times 1 is x plus 1 times y plus y. That handles the first value over here. Taking the second row, 0 times x plus y times 1 is y. So that would be the result of this shearing transformation. And where does the blue square is going under this new matrix that I just listed. Somebody, please. People? Oh. Not bad. Let's hear more opinions to see that there is a consensus, because I interrupted you when you just started discussing. 0, 0, same 0, 0 over there. What happens to it when it multiplies by this matrix? Stay in 0, 0. What happens to the x value of a point? The x value, write it down, x goes to x, while what happened to the y goes to x plus y. So points will shift upward, and the more to the right you are, the more higher you go. Right. So as opposed to this matrix, to this transformation in this case, this will go to, help. Let's do edge by edge. E1, E2, E3, E4. Where does E1 goes? E1 goes nowhere. Happy where it is. So E1 is the same E1. What about E2? Does it change its orientation? No, it stays parallel, but it goes upward to somewhere here, and E3 and E4 are going to this point, and this would be 45 degrees. Cool. Yet another example of shearing, and shearing doesn't have to be 1 at this point. Changing the 1 would just, replacing the 1 by some other number will just change the angle over here. And before we leave it completely, you look at the transformation. How do you know if it's shearing or rotation? Right. In terms of invariance, what stays the same, what should change? Shearing matrix, it might be correct. I'm not putting my neck, but I think that you are correct. Yeah, but just look at the images. I mean, the matrix, you are right, but you might be right, but I'm not entirely. Yeah.
For shearing, angles are not preserved, but parallel lines are.
Everybody heard it? That parallel lines go to parallel lines in both rotation and shearing. Angles in shearing, this is not 90 degrees. Well, and once again over here, I wasn't sure if I have this slide or not. Yeah, let's give you time. Just the same shearing that you do over here, and that this matrix captured. But it changing putting some coefficient here, as I said, changing this value to alpha. As long as it's positive, it will still go up. Could be negative. Just as well, could be different than 1. Okay. This matrix, this is the first time that we saw multiplication of two matrices. And we can spend some time and compute what is a multiplication. So x prime, y prime equals to the take xy, multiply by m2, takes the result, and multiply by m1. And you can compute what's happening by what I would strongly discourage. Compute the product of these two matrices and look at the numbers, or let's try to understand what happens to xy. I take point xy, multiply by m2, and the result will be, it is, what's the name? Scaling. So that was scaling. And after I took the scaling, that takes 6x, move to 3, 3. Now I multiply by m1, so the order is from right to left. Now I multiply by m1, that you know that it's down, that one slide ago, 2 slides ago, we saw that it does the shearing. So it's scaling followed by shearing. Cool, and hopefully everybody appreciates the animation that you see right here, where the clock almost didn't move at all. So that would be the result. Reflection, get another one to the catalog, why not? X, y moves to x, but minus y. 0, 0 goes to 0, 0. And what is this? 1, 1. The x stays the same, 1, but the y that was 1 becomes minus 1. But so just I took the image from here and flipped it to here and multiplied by, again, by the same matrix. We'll just reflect it back. Let's put I have a question that I didn't think about this matrix. What was it? So it's x stays with x minus 1. Sometimes I'll just write the matrices. It's common to all the 0 values will not be written. This matrix is just 1, 0, 0, and minus 1. So multiply by xy, x stays the same, y becomes minus y. And I'll ask you a question about this matrix a bit later. Why my obsession about matrices? Not my obsession, graphics obsession. You all know the answer, but here it is written. Your hardware is well optimized to do multiplications of matrices, of vectors by matrices. It can happen in parallel. It can happen when a lot of the operations are already burned into your CPUs, GPUs. Your hardware really wants you to do everything as matrix operations. That's what it optimized to, and very good in parallelizing. If you have a lot of points in your geometric scenes, your GPU would, as much as possible, prefers to work on all these points in parallel, which would somehow boils down to be matrix calculation and maybe more than one matrix. Okay, so we have a transformation, which might be one of our very basic transformations, the Lego bricks that we are building, rotation, translation, etc. Or it can be some composition of transformations, and we would like to calculate a single matrix, as long as it's the same transformation, that will work on every point that we need to handle. But if I want to create a geometric scene where the camera first look at this direction and then the camera will change its orientation to look at this, I'd much rather, instead of having many points on every point on the surface in this room, just every point that I see multiplied by the correct matrix to recalculate where this matrix is, instead of really changing the location of items in the room. I'll change the prisms, the way that I see each point, by shifting it, and the shifting will be applied, or the transformation will be applied by every data point. I'll multiply by a matrix, and it will save all my operations, and as we said, my graphic hardware will like me. Pulling out some basic properties of matrices. Hopefully this is true. A times beta plus C equals, for every matrices for which a product is defined. As you know, product is defined, hopefully. If you don't know how to multiply matrices, please remind yourself. Matrices are defined by taking one row for here, multiply, taking the ith row from here, the jth row from here, and that's in the product would be the ijth element that I'll write over here. And then I'm just doing the dot product between these two vertices. And of course, I multiply matrices only when it makes sense, where the number of columns here equals to the number of rows here. Okay, distribution property. A times B plus C equals A times B plus A times C. And now I multiply 3 matrices, and I can multiply them when I see the notation A times B times C. Doesn't matter if I'll compute it as A times B times C. That is, the order operation doesn't matter. The order of the matrix matrices doesn't. A, B, and E does not equal in general, or might not be equal to BA. That is, it's not always equal. So the order of the matrices in the product does matter, but the order of operation, how you calculate it, what you're computing here when in A times B times C equals A times B times C. Okay. Identity matrix, talked about it last time. 1, 1, 1 if I'm in 3 dimensions, or 2 dimensions with homogeneous coordinates, so I need 3 numbers. 1, 1, 1, everything is 0, identity matrix. What's special about it? Multiply it by any other matrix that it's legal to multiply, and it doesn't have any effect. It's like multiply by 1. And some of the matrices, it will be quite common, but not always in this course. Almost always, but not always. In this course, when I'll generate a matrix, I'll have its inverse. What is the inverse of a matrix A? A minus 1 is a different matrix, sometimes different matrix, such that A times A minus 1 gives me the identity matrix. Yeah. When I multiply A from the right. Okay, so that would be the inverse of this matrix. And our first claim would be that if I take A and take A minus 1 that I defined as multiplication from the right, now if I'll multiply A, but from the left, I'll still get I. Why? And that's very cute. To prove, let's write A times A minus 1 times A. Where do I put the parentheses? Doesn't matter, but distribution law. So I can write it as A times A minus 1 times A. That's, what is this expression? By definition, this, by definition of A minus 1, A times A minus 1, this gives me I. I times A is just A. Now I wrote A times A minus 1 times A, but now I put the parentheses on the right, and A time equals A times something else. How could it be? What is something else must be? It must be the identity matrices, otherwise this would not work. Okay, makes it easy using the distribution matrix. How do I compute the inverse matrices? Well, if I need to compute the inverse in general in the real world, I need to solve some linear system of equations, diagonal the matrix, the Gauss elimination, some various sets of operations. You don't need it mostly in this course. Why? Because most matrices, it will not be that hard to compute the inverse. You will want to compute the inverse sometimes, but as a possible way, but mostly you'll have some geometric rules that will help you understand what is the inverse. For example, what did this guy do? Now this is A. And to remind you, A took a point here, this person over here, and flip it, not changing the x value, but flipping it upside down. So A minus 1, in this case, the inverse of A. Very, very challenging question. Of course, course, as we said, we can solve system of linear equations to compute it as you know to compute inverse of a matrix, but in this case, just somebody else. For A minus 1 is just A. Prove it in two ways. One way is just multiply A by itself, and you'll get the identity. Another one is geometric reasoning, right? If I move this person from blue to red, flipping down, flip it up, well, you'll just flip it again, you'll just get it back to where it was. What about this matrix? Let's give it a different name. It's S. I'm sorry I didn't get to the webcam from the OBS, so it's not in the recording. Sorry. For this S, what does this matrix do before we just to check that you're alive? We're scaling by twice. So scaling by 2, thanks, yeah. Multiplied by size by 2, so S minus 1 would be there. Oops. Just scale by, well, scale by half instead of double the size, shrink the size by half. Okay. So in this case, it's easy. Play with the shearing, also easy. A very challenging question. Three questions. What is matrix do geometrically? Take S, every point, x, y, and what happened to this point P, given the x, y? It is landed nicely. Just so keeping its x value, but its y value vanishes. Implying that if I have P prime over here with the same x coordinate, it will land on the very same point. It's orthogonal projection. Meaning that there is no chance to find an inverse, because inverse should have placed these points back to where they were. And there is no way to distinguish these 2 points. So obviously this matrix doesn't have an inverse, which you can convince yourself also by noticing that its determinant is 0, if you remember what's determinant. Rotation, let's play with this a bit. You'll see more rotation in this course than you probably want. I want to rotate, and at the moment I'm rotating it around 0, 0. So I take the point x, y, I decide about the angle theta, always counterclockwise. Always counterclockwise direction. So how do I rotate by theta? Yeah, this is my rotation matrix. I now need both the x and the y coordinates, and I'll give you a few reasons to believe me why this is true. Rotation matrix by theta is cosine theta minus sinus theta. Sinus theta and cosine theta. That is the new x value equals to the old x times cosine theta minus the y value times sinus theta. And the new y is x sinus theta plus y cosine theta. And you'll need it for homework 1. And once again, here is the new x value. Here is the new y value. And we can see this formula from different ways, and it's good to understand where it's coming from a few ways. So, oh, I forgot the animation. How do I rotate a point? Here is a point P. I want to rotate it by theta. How can I represent P? I can use Cartesian coordinates, x and y. It's AB. Another way to represent P is to think about its distance from the origin. Its distance from the origin, which in this case, let's say it's 1. And, or I can, sorry, I still in the Cartesian coordinate. Its distance is 1. And now what is what is A here? It's cosine of something that depends only on theta. Let's call it phi. Cosine of phi, that's a x coordinate, and y will be sinus phi. Phi is something that depends only on this point. But I'm not rotating only this point. I'm rotating the whole world, the whole clock that you saw earlier. So every such point, I want to rotate by theta. So what happened to the point P? What would be its new cosine, its new x projection? It will be cosine of the old cosine. Before that, it was cosine of phi. Now it's becoming cosine of phi plus theta. And then you're checking the textbook ChatGPT, and it tells you that, oh, there is a formula to sum of two angles. Cosine of phi plus theta is just cosine phi cosine theta minus sinus phi sinus theta. But what was cosine of phi? That was individual to this point that I started this story with. Cosine of phi was individual for this point. That was just the x coordinate of this individual point. And sinus of phi, this value, is a y coordinate. So that's why the new x value would be the x coordinate, a times cosine theta, the rotation angle, minus b, the y coordinate, minus sinus theta. Again, a and b was individual to the point that I took, but theta was where everything goes. And the story for the y will be analogous. I think that's a most boring way to justify this notation. And in this case, I assume that this point P satisfies a squared plus b squared equals 1. Pythagoras will tell you that it means that x squared plus y squared equals to this guy square equals 1, meaning it's distance 1 away from the origin. If it's not distance 1, then it stays in the same distance from the origin, just rotate it. Okay. Yeah. So just to write it down, r of theta is, as we said, multiply cosine phi times a minus theta t b. That will give me the new a prime, and similarly for the b prime. I don't think that this joke was that funny. First time I heard it, or you heard it, and that was a long time ago. You have a mathematician. Mathematician stays here. There is a coffee pot on a table. Over here, there is a fence. Along the way, the mathematician wants to pour some coffee into the cup. Algorithm, go bring the coffee cup, the coffee pot, coffee kettle, bring it to the other side of the fence and pour the coffee into your cup, and you're done. Problem solved. Next problem, you have an empty table, fence, table with a coffee pot and mathematician and coffee cup, coffee kettle, and you want to pour the coffee into the cup. Solution, bring the coffee pot cup to the other side, and from this point you know how to solve it. So it wasn't that funny when you heard it the first time. I just try to say, let's recycle solutions that we know how to solve it. I'm trying to justify why we are going to break every problem, like computing the translation into computing transformation into basic elementary things that I already know how to solve. For example, I want to resize the clock, but if I'll resize it right now, its center will change. Scaling the clock right now will move its center. I want to enlarge this clock, but without changing its center. How do I do it in light of this non-funny joke? Earlier, I will bring it to a problem that I know how to solve, which is let's shift the clock so now its center is at 0, 0. At this point, I'll scale by 2, making it twice as large. And now, knowing the transformation, the translation that brings the 0, 0, that brings the center that used to be at 5, 5, bringing the center into 0, 0, look at the very same transformation and now apply the reverse, the inverse transformation, which take 0, 0 back into 5, 5, but now it's an enlarged clock. So I'll need 3 matrices to solve it, except the middle one will be the multiply by 2. Everybody understand what's the problem that I'm trying to solve? If I'll scale the clock in its original place, the center will change. I want to enlarge the clock, but in its environment should stay the same. Right? So I need to move it to the origin, scale it by 2 then, and then move it back. And I want to do it via matrix multiplication, except that I cannot. Every matrix multiplication is a linear transformation. Linear transformation A multiplied by xy. What happens if xy 0, 0? No matter what my matrix A is, still takes me into 0, 0. Not very helpful. In particular, if I want to move the center of the clock A from 0, 0 into this place, no, I cannot by a matrix multiplication. But I want to solve via matrix multiplication, so there is a solution. But it involves making everything that was intuitive and simple into possibly less so. Before I do it, here is another story. I want to rotate theta around, I want to rotate the house, but the center of rotation should be the corner of the house. I don't want to rotate around 0, 0. We have a rotation matrix, but that will not be the same. I want the corner to stay where it is. P should not move, while if I'll rotate via the rotation matrix that we just saw, P will definitely rotate to some other place. So how should I do it? Take the whole scene, translate by minus P. Take where is P? It has X value, Y value. Shift every point by, take the X coordinate, add to it minus the X of P. Same goes for the Y. So the corner of the house becomes 0, 0. Now it's okay to rotate, and now apply the inverse transformation. Yet another one of the story justification. I want to reflect the house, but reflect around this line, the baseline of the house, which is not the x-axis. How can I reflect with respect to this house? To this line, I'll calculate this line. I'll find its y-intercept, which is minus b. Need to calculate it based on the formula of the line. What next? Translate everything so everything goes down, and in particular the house moves vertically down so that the line intercept is now at 0, 0. What else? That was just the first step. what next? Now rotate by, what did we say? Rotate by alpha is rotating counterclockwise, always counterclockwise. If I want to rotate this thing clockwise, it needs to be rotated by minus alpha. Maybe we'll wait a second. If R if that's R, another example, R minus 1, the inverse of R, would be from geometric arguments, the inverse of rotation by alpha clockwise, then the inverse should be rotating counterclockwise. So it would be rotation by R minus 1 is cosine minus alpha, sinus minus alpha, minus sine. I will not get to homework 2 today. Minus 1 is cosine minus alpha minus sinus minus alpha, and so on. Sine minus alpha and cosine minus alpha. But again, just geometric calculation. Back to our house. Shift it down. Now rotate by minus alpha. Now I am allowed to reflect the house via the matrix that we saw earlier, the flipping matrix of moving y into minus y and don't change the x. And now do in reverse order, the order matters, everything out there. It sounds complicated, and it's, what is this? It will become a multiplication of 1, 2, 3, 4, 5, 6 different matrices. But once I'll compute each one, it will be very easy to compute its inverse, A, and B, I'll calculate all this product of 6 matrices only once for the whole operation, and once I have the resulting matrix. I don't care how many steps it takes along the way. Now it's only a 2 by 2 or 3 by 3 matrix, and it's very easy to apply it for the billion of points, and it definitely justified the time. Okay, so brings us into concatenation of operations. Just to remind you, A times B times C equals A times B times C. So the order doesn't matter when I don't need the dot here. When the context is clear, I'll just avoid the dot. And if I have multiplication of matrices, then if I want to apply M1 on P and then apply the next one, I can, I can just compute the product of the 2 or 3 matrices, calculate it once, and let your graphic handle this product for the billion of matrices. Let's talk about homogeneous coordinates. I need to do translations. All these scenarios that I had before all ask to do translation via matrix multiplication. And to do it, I need now to think about redefine what is the location of the point, or how do I read the triple of numbers 4 to 1. I have 3 numbers 4 to 1, but what does it mean? It is a location of a point in 3 dimensions, maybe, but not right now. I need to tell next to it, is this in Cartesian coordinates, or is this in homogeneous coordinates? The triples of numbers 4 to 1 meaning very different things in homogeneous if they are in homogeneous coordinates, or they are in Cartesian coordinates. 4, 2 in Cartesian coordinates is just a point whose x coordinate is 4, whose y coordinate is 2. How do I understand x, y, w? 3 numbers, but now I'll tell you that this point is homogeneous coordinates. There are 3 numbers. The point lives in 2 dimensions, not in 3. Despite having 3 numbers, the point lives only in 2 dimensions. And if I'll have 4 numbers right here, it means that my points live in 3 dimensions, 1 dimension less than the number of numbers. How do I understand this triple of number x, y, w? It's a point in 2 dimensions whose x coordinate is, look at the last one, that's w. X, the first is x divided by w. The second is y divided by w. And w is not in the game anymore. Again, justification to all this gymnastic is because I want to do translation via homogeneous coordinates, which you still don't know how. I still didn't tell you how, but at least that's a first step. So if I want to write a point 4, 2 in Cartesian coordinates, I can write it as 4, 2, and w that you see here, and w is 1. So 4, 2 in Cartesian is just like writing 4, 2, 1 in homogeneous coordinates. It's the very same point. Except that in homogeneous coordinates, I have more ways to write the very same point. The very same point can be also written as 8, 4, 2. Why? Because it's the same point. Because to understand what this point in 2D means, if that's in homogeneous coordinates, I'll do this exercise. Take the last one, that's your w. 8 divided by 2, giving you 4. And 4 divided by 2, giving you 2. So it's the same point, 4 to 1. I can also write the very same point as 2, 1, and half, because 2 divided by half is the same 4. Okay, so same point, the same point, multiple ways to write the very same point. Why is this good? I'm not there yet. Yeah.
What is the, why is it useful?
Because otherwise I cannot do translations, and otherwise I cannot do perspective projections, that is still way ahead of us, but perspective projection, when I want to ask, hey, here is my screen, and here is an object in 3D. Based on the coordinates of this object in 3D, I want to multiply by a matrix and find where it is on a point on my eye. So here is my eye. That would be a center. That would be our scenario. Here is my eye. Here is a point in 3D. You just see the depth, the z, and the y. X vanishes. How can I compute which pixel this point will go to? I need to compute to use triangle similarity. That's the screen. That's some object in 3D. Where does it go to? I need to divide this divided by this equals this divided by this. So knowing the distance from the screen and the x, y, z coordinates, I can compute this point. Great, but I want to do it via matrix multiplication, which division, again, will call for this operation. But it was, it's not something that it's not as fair the last time that you see perspective projection in this course. Not that I expect you to know what I just said. Okay, but at least as an agreement, when you see 3 numbers in Cartesian coordinates, you know how to express them into point in 2 dimensions. If you see four numbers and I tell you that it's Cartesian coordinates, you understand how to express it in 3D. Always take the last one, and that's the denominator of the other numbers. When you tell your computer about a data point, you can always say this data point, the last number is 1. But if you see an output of your computer and your computer says this value is in homogeneous coordinates, that's how you understand it. It splits 3 numbers, takes the last one, and that's the denominator of the first 2. So 4, 2, 8 in Cartesian is a point 4, 2, 8, 1 in homogeneous coordinates, which is also the point 8, 4, 16, 2, also in homogeneous. This and this are the same. Why? Because take 2 as w and divide the first 3 by 2, and you're back to 4 to 8. And now I answer your question. So I have a point x, y. I have a point x, y. I want to convert it into homogeneous coordinates. What did we say? That if I know what is x, y, and I want to tell my computer about it in homogeneous, my last number will be always 1. Okay, so x, y, 1. And now I wonder what happened to it when I multiply it by the following matrix. And this matrix is 1, 1, 1 along the diagonal, so it's almost identity, except that notice what happened here in this last coordinate. It's alpha and beta, some two constants that I assigned to this matrix. Let's do this trick. Let's do this multiplication. It's trick, like to think about it. xy1 times 1, 0, alpha. What do I have in the first value? 1 times x, x0, plus 0 times y. You don't see y over here. Plus 1 that I gave times alpha. So it will be 1 times alpha. So x0 plus alpha. What is the y coordinate? 0, 1 beta. 0, 1 beta times xy1 is what? It's 0 times x plus 1 times y. So it's y plus 1 times beta, ending beta. What happened in the last coordinates? It's 1 times 1, give me the 1 back. What's the impact about the xy? What did I get in return? I translated it into this point. You'll have plenty of GeoGebra stuff to play with. So if you open an account, free. Not showing me. Here it is. Here is M. M is right now identity matrix. What happened to my points? Hard to read because the identity matrix just take a point and leave it exactly where it is. So the red point stays a red. Green point over here stays where it is. You see, 2 copies of the green. Help before I click return. What would be the result? I changed this value to be 5 instead of 0. Yep. Look at this formula. I change it to this value to 5, so the result would be that I'm shifting the point into x plus 5 constant. The beta was 0, so I shift all the points now by 5 to the right. A bit hard to see. Let's do it a bit more extreme. Okay, source shifted to the right. Blue moved to C, moved to C prime, and B moved to B prime over here. Sanity check. About to click return. What's going to happen? Going down by 3. What about now? Well, not somebody else. It was 1. Now I'm about to make it 2. Changing this to 2 will split the point x plus alpha, y plus beta, 1 times 2. So the last coordinates will be increased by twice, which according to our understanding, that's x, y, w should be read as in homogeneous is x divided by w and y divided by w. In Cartesian, so what would be the impact? Having the w as 2 instead of 1.
Is it effectively as if we were scaling everything by 1/2?
It's exactly scaling by half. But think about the x, y, z. Over here, the alpha, beta, gamma. Let's make it actually the opposite way. Half will make everything twice as large, in addition to the translation and rotation. The translation and rotation are still here. Cool. So now we understand homogeneous coordinates and at least one idea how to translate it. So if M is A, B, C, D, and 0, 0 all over the place, then M times XY is just like ignoring this row and column beforehand. So we had the most transformation, excluding the all the transformations that we saw, excluding the translation, all the other transformation, we could express as simple 2 by 2 matrices. They are still alive, just when you need to use shearing, rotation, and so on, just keeping everything as 0, 0, 1, 0, 0, 1 as the last row and column. It will be the same effect. All these matrices are still there. So half, half xy, scaling by half, is just like in homogeneous coordinates, half, half, and the last one becomes 1. Okay, just keep the last row and columns. Okay, and on the other hand, if it's half, half, and 2, 3 as the last column, it will mean that you first apply the alphabet A, B, C, D, the shearing, rotation, or the scaling by half, and then translate, then you're using as a fact the two numbers that you wrote in the rightmost column, which applies a translation. Okay, back to our rotating the house around the corner. What would be the matrices that I'll use? Again, it looks like a lot of work, but think about it as you're computing this product of 3 matrices once, and then you send it to each and every corner of the house. If you are using fragment programming, we'll do it later in the course, then you are sending the vertices of this shape, and your GPUs will set all the details of everything that is not a vertex of these triangles. What are these matrices? What was the algorithm to rotate it around C? Take it, shift it by minus C, so now its corner is at 0, 0, rotate counterclockwise, and put it back in place. That is, translate by, if this was translate by minus C, if translate by minus C, move C to 0, 0, then the reverse translation is translate by plus C. So assuming that C is x, that C is at x0, y0, then multiply this by xy. Where my hand is, that's the point, every point xy, including C itself. First, I multiply by this matrix, which is what? Translation by minus C. The result is multiplied by this matrix, which is rotate by theta. Rotate by theta around what? Around the 0, 0. But it's fine because 0, 0 now contains C. And translate it back by plus C. Cool. So the product of these three matrices. Okay, of course, practically you can ask JetJapat to do some of the work from you. You can ask the libraries to do the matrix multiplication per se. It's not that I'll ask you to always do it, and you'll have code for matrix multiplication, etc. But at some point of time during the course, I'll ask you to understand how each one of these matrices actually works by itself, without boiling you with tedious arithmetic, but what each one should do by itself and why does it do what it do. You need to understand. Okay, quick quiz. What does this one do? This matrix? Nada. Keep every point by itself. Is this homogeneous coordinates? No, it's just two coordinates, Cartesian. This one, flip by, take x to x, flip by y. This one, flip by minus y. X stays minus x becomes minus x, y stays y. Right. This person, I'll give them its right arm is much longer, goes over here, and now this long arm becomes this long arm. This one, say it, shearing, and this one also shearing. This one, meaning what? Where this guy goes? Sorry? So this guy will go to, this person will go to, right? I flip by x and then flip by y. That's a, right? Because now it's 1, 1 or minus 1, so in the result I divide everything by minus 1. And this one, we played it, scaling by, make it smaller, larger, larger, because I'm dividing it by a smaller number. Yeah, identity matrix, we saw it, we had this discussion, m times I equals I times m, the identity, equals the one matrix. And for all the matrices we have seen so far, we had an inverse, m minus 1. The inverse of this one, for obvious reasons, inverse of this one is like in every semester in some exam or another, I'm asking questions like to questions like compute this matrix to the power 1,000, 100, and the result will be, let's let everybody think about it, the result will be, very proud of this type of questions. Yeah. Right. If that's a, then a to the power of 100 multiply a to the 100 times p is just like white. A times dot 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 a, all of it times p. A times p will be shift a by 3 and 2, right? Multiply by a, shift by 3 and 2, shift by a, multiply. Shift by 3 and 2 all the way, and you're doing it 100 times. So it would be 1, 1, 1, and 300 and 200. Right. Okay, and the a to the minus 1, if I shift by 3 and 2, then a minus 1 will be minus 3, minus 2. Let's be happy with, you can prove, if you like, complex number, you can get into the notion of the rotation also via complex numbers, which is cool, but where we'll refer to it is that it has a simple extension that where in graphics, somebody? Tell me. We'll need a system of things that when we'll apply them to each other will give us a nice way to interpolate rotations. And why do we need to interpolate rotations? Because we need to do animations of something that move from this position to this position. And if it's linear translation, if I translate, then interpolating linear transformation shifting is very easy. To interpolate rotations, a lot of strange things can happen. But if you think about rotating between 2 points of a sphere, how do you go between 2 points on a sphere? It sounds quite easy if you are in 2D. In 3D, strange things can happen. And there are solutions to it that at least we'll mention, not extremely. If you want to Google for it, check for gimbal lock, and it will lead you to the solutions and why things that are obvious are less obvious. Let's start talking about homework 2. I'll wait with homework 2, which is just to remind you, you need to read a file. You'll have all the libraries that does hard work, reading a file name, reading your folders, everything you'll get from Amir in GitHub, and then it starts rotating. Okay, maybe I'll ask you to scale it, maybe not to scale. In this case, you don't scale. If you don't scale in its full size, then it will lose its corner when it's vanishing. So you also need to scale it as it goes. And I'll still clean a bit the GeoGebra, but let's play a bit about what's the main algorithm that you need to do for this rotation. So what you'll have for some specific theta is that you will have an image. Say this image consists of one blue column, one red column, blue column, red column, and so on. So that would be your source image. And part of the parameter of the source is how many rows and columns you have. That will be in your header file, and that would be very easy. And now I want to say scale it, and maybe it's not even the same number of rows of columns. That would be the result that I'm going to have. So maybe I only scale it to a different number of rows and columns. So what used to be pixels are not exactly pixels. These black dots are where I'm sampling this image. I want to ask what is the color at this point? What is the color of this point? Because this point is exactly where one of the output pixels, that's my target pixel, that's exactly where my target pixel is going to fall in each one of these points. And at each point, I need to guesstimate what is a color. And when you're guesstimating what is a color at this point, I can think about the source image, and we said that every pixel have 2 lives. A pixel can be thought of as a point of sampled, which is like how I report the output pixel, or I can think about a pixel as something with area, little square rectangle that has some area, and a point falls inside this pixel. And now a pixel in the target wants to know what is its color, that the color of this pixel is right here, better in the other app that I had, that you'll say, here is my target pixel over here, and for this target pixel over here, and this is my target image, my output, I want to know what is a color right here, and how should I do it? I'll calculate what is the point here that this transformation will take me from this point. Doing the transformation that I'll describe to you in a second, just in reverse. this transformation that essentially does the following, taking this shape and somehow moving this shape from the source to the target, except that they are not exactly aligned, but that's the idea. That they are going from the whole image from the source, and then it needs to snag eventually into the target. And then once it's snagged in this mental image, I can ask for every target pixel, hey, target pixel, where are you coming from? You're coming from some point in the source image. I'll copy the color from the target, but in the right place. That would be the whole world. I'll calculate the target in the right place and copy the color over here. How do I know what is a color right here in the source if it's in between a few pixels? More commonly than not, it doesn't lie exactly in a pixel, but it's, if you think about input pixels are points that are just sprinkled, the source will be a point that's somehow between pixels. And I can just ask who is a nearby pixel, if I think about pixel as square, who contains my source. And then I can solve it by just tell me who is the nearest pixel, and I'll just copy the pixel. Or I can say, hey, it's cool, except that now I am getting a very jumpy staircase like images. We'll have a name for it. It's called aliasing. That's if I sampled it by some pixels. Or you can say, if I'm between blue and red, then my color should be some combination of blue and red, maybe some average of blue of red. And if I'm closer to the blues than to the red, then it will be some weighted average. And we'll talk about anti-aliasing technique that will say that a color of the output, a value of output pixel, does not need to be necessarily, or better not be necessarily, a copy of a input pixel. It could be some other combination that is averaged of a few pixels in the nearby vicinity. And that's why when you'll ask if in MATLAB, how do you do rescale of an image, it will ask you, oh, but your interpolation, do you want to look at the nearest neighbor interpolation, which is the quickest, but can create more artifact that would artifact like what? Here is a black or darkish strip. And now I want to render it using very few pixels. Only 9 pixels in this input image, which will make me have to have this pixel, if in this case, either fully black or fully white. So my results right here from this pixel would be this very strange shape where everything here is ended, and these boundaries are very noticeable. They are very sharp. Of course, you probably don't want to use 3x3 images, but you notice it even if when you are resizing an image to a smaller resolution. Is this always annoying? Not always equally annoying. It will be annoying for this image when your image is static, but it would be highly annoying and very noticeable in animation of videos. If the shape is now moving and suddenly this pixel that until now was fully white because it has very little intersection with this the input shape, the shape is moving slightly upward, or the viewer is moving slightly upward, and suddenly this pixel turns black as well, and this flickering effect are extremely noticeable in a very high resolution of your screen. What's the solution? To say that the color of this pixel is not necessarily fully black or fully white, even if the image was, but it could be grayish depending on its vicinity to the shape and what's the color in the area. You don't have to worry about it in homework 1 about aliasing, but something to keep in mind and maybe read more about in ways to prevent aliasing effects. In homework 1, nearest neighbor interpolation is fine, but still you have fair amount of calculations to do. So I have my inputs, I have my output image living right here with some number of rows and columns. Even without translation, I have my input image, and I need to compute a matrix that will take me from every point here to every point here and vice versa. From this point to this point, then the reverse transformation will take me from this to this. And remember what was the main source of the bugs that I mentioned last meeting. Having a loop that runs on the input image and copy it into the output with taking for each pixel here, where does it go to, that's doomed to create a lot of artifacts in many pixels that you left unfilled. Correct way, have a loop to the output pixel, have a loop on the output image. Here is one pixel in the output image. Ask, hey, pixel over here, where are you coming from in the source image? Where am I coming from? Copy the color to this pixel and move to the next one, move to the next one, move to the next one, and so on until you fill the whole image. And that's how your image should look like at a source with no rotation, of course not for strips, you have bunnies and other examples. And once you rotate it, then now, of course, what used to be the blue strips will become horizontal. But there is stuff to study about the computing the transformation that takes me from the first one to the second one. And though it's tempting to find shortcuts, the main rule is always go to the unit. Always go to canonical volume. What is a canonical volume, or the canonical image, when I want to have all my transformation happens in? I'll go from, probably prefer a different marker. Here is my x and y, and I go from y to y minus 1, y equal 1, and x equals 1, x equal minus 1. All my transformations will assume that both the output and the input happens in this volume, in this canonical volume of minus 1, 1. And in 3 dimensions, it would be the canonical volume and not the canonical square, because it would be minus 1, minus 1, minus 1. Your graphics will like to think that it happens. You don't need to actively move every point there, but once you'll calculate your transformation and feed them to your computer, it would like to assume it. So that's why these strange graphics that I work so long of doing, GeoGebra is fine, but having animation is a huge time sink. So you're taking the image and we'll find a transformation that map it into the canonical volume over here. And we'll do the same for the target. Everything happens in the canonical volume. And if my image needs to be rotated, all my rotation pixels, all the source pixels, will be all sampled over here. It will be way easier to debug. Even though it sounds like a unnecessary headache right now, much easier to map everything into this minus 1 to 1 in the both x and y. And that's a consensus in the graphics. So we'll figure out what are the matrices that does the job for us, which would be take your input image and map it into the minus 1, 1, the canonical volume over here. How can I do it? Given the number of pixels over here, I'll first shift it so its center coincides with 0, 0. If there are 100 pixels, I need to shift it by roughly. There will be a little noise, but if there is from 1 to 100 pixels over here in the input, I'll need to shift by Help? You want to go home? What? What? Need to shift by negative 50 roughly. And if I have 300 pixels here, then I need to shift in the vertical direction by minus 50 by 300 divided by 2. Plus minus half. That will be very annoying, plus minus half. So after this shift, now this part nicely stands. So its center is at 0, 0. And now, independent of what was the number of rows and columns, we'll scale it. So now it's snag to 1 and 1. And that would be one matrix. And we'll do the same trick for the target matrix to also be on 1, minus 1, 1. And now for every target pixels, let's compute what is its source pixels over here, which I don't do it formally. I just compute the matrices. And the same matrices in the opposite side will take me to a point over here, and I'll just need to monitor its color, copy it into this. Okay, sounds a clear way, but much easier to debug. And pieces of it later on will switch to do it via libraries that will help to do it right here. But homework 1, we are down to the foundations. Thank you. We'll talk about it, of course, much more. I don't expect you to fully understand it. So I'll delay the submission date accordingly. And we'll also talk a bit. Show me hands how many people knows JavaScript to some amount already and have it implemented. Let's say how many, okay, like have Visual Studio installed, played with. So about a third of the class. Oh, show me hands if you don't have any experience whatsoever with JavaScript. Okay, so we'll have some introductions, but will not be the same. At the meantime, play a bit with this at home. Some people like Visual Studio, some hate it. You don't have to. You can use different editors. There is reasons why to do Visual Studio. Implement some and download some JavaScript interpreter out there. And yeah, get some basic advantage, but we'll scan it in the next meetings as well. And WebGL will get there later. We'll get in this course, but a much later stage, or at least later stage. Thanks. Yeah.
Do you have the class website or something? Because I noticed there's nothing on the Piazza nor the D2L.
That's strange. I published, unless I may.
Because I don't see like a separate item.
Okay, I thought, didn't I publish today that a meeting is here? At least.
There's nothing in the announcements besides the welcome board. The link to I was wondering if there's something in the syllabus that led me to a class website, but the link is bad.
Go to my website.
What is your website?
Alon Efrat. If you look, www.cs437.com. That's it. Sure. In my
www.2.
yeah.
cs.arizona.edu
But why didn't it? Okay, that's strange.
You were talking about assignment 1, and I was just worried that I'm missing.
Don't. Yeah, on Piazza it's a big deal. So give me a sec. website. Yeah, that's where you see the material. But now let's see what happened with Piazza. Because I so do you in you see so at least this one and let's publish again the course parameters. But Piazza is the main communication.
Yeah. Is Piazza we're going to be posting the assignments too?
It will take you to overleaf links.
Overleaf? Yeah.
I
So
just deleted. I had the whole last year's homework that I think that I just removed. One thing at a time. Let me.
So should I expect to see the homeworks posted onto Piazza through Overleaf?
Yes, there will be an announcement homework one, etc. Let's see that you are getting to the course website. Yeah. But so yeah. So bookmark the course website at least. And there was an announcement on D12. Why you don't see it in the announcement? I'll check it offline.
Yeah.
You're in a hurry. Yeah. This link is.
That's just Piazza.
This.
Oh. Okay. And then have you posted assignment 1 yet or no?
No.
No?
Okay.
Okay.
Not yet. But probably at the end of next class, I'll need to cover a big JavaScript. We'll cover it and more of the algorithms behind it. So probably. Yeah.
I heard you talking about it, so I was worried that I was missing assignment 1 already.
Yeah, that was my question as well.
No.
Okay.
It's not. No, and I'm usually very flexible with that. Hey, you didn't forget your record, your
Yeah.
letter, and we'll do it today.
And I had a question about
Sure.
the last part. So when you do the transformation, you have to move it to the center and then rotate it or whatever. And then when you map it back, how do you prevent last lecture you showed us how maybe some pixels were empty or
Well, sure.
Or
So
how do we,
in terms of transformation, I think about it as so I don't want this whole argument, but here is a point Q of the target. I first translate the target. So what I want is this matrix. What this matrix is doing is taking a point of the target. Now do shifting of the target, so its center is at 0, 0. Scale the target to the 1 by 1, rotate it. The scale by 3 we'll get to in a second. It will be a bit harder. And now this applied the opposite to the scale and applied the opposite to the for the source. For the scale and then the translation. What did I get from here? If this is a point here in the target, here the image actually lives between pixel 13 and something else. I don't care. For my point here, it will map me to a point here, and I will ask for this point here. So I don't move necessarily the pixels to the unit square, but the whole translation, the whole calculation of the matrix is done based on the assumption that I will not jump directly, but I'll take it into the unit square. Why? It's not hard to do the linear translation directly, but now you are adding to it now in the unit square, you will add to it the rotation, and now with the rotation to make it all correctly, it would be a nightmare unless it's in the unit square. So that explains this rotation. But again, at the end you're ending up with one matrix. So what does that if my image was here and here, I need to shrink it a bit so it will fit to the unit square. And then, so it needs to do this shrinking and enlarging, and that's
And then
one
you
more.
map that back, right? Or you transform it back to.
So that's yet one matrix. So, but when I had this product of 7 or so matrices out there,